if electrons behave like a tiny magnet, then I can use giant external magnets and try to put a turning force on it. If I use a giant external magnet like this,
keep in mind he's over exaggerating when he says if it was a giant, giant meaning it was powerful. I'm sure they're giant, but they're not powerful. If they were powerful, a magnet would just fly to one side or the other, okay?
Then the poles repel each other, and look, these forces are trying to turn my electron tiny magnet. And now, if the electron does not have any angular momentum, then we should expect the electron to just succumb to that turning forces. On the other hand, if the electron does have some kind of an angular momentum, right, which resembles spin, then it wouldn't turn. Instead, it would just wobble like this, and then we would know that it has angular momentum. And how do we actually detect it? Well, it turns out that you can actually shoot electromagnetic waves and figure out whether the electrons is wobbling or not. We did this experiment, and guess what we found? We found it wobbles! Electrons wobble! Does it mean?
You'd think at this point they'd be like, oh, it does spin. It has an intrinsic spin, velocity. And that's what makes the magnetic, field. But no.
Well, it means one and only one thing. Electrons have angular momentum. There is no escaping it anymore. They have angular momentum, because of which they can resist turning forces. They can resist torques.
But they still ain't spinning, are they?
And the precession that the electrons possess, if you want to look up, it's called Larmor precession. So you can look it up and you can look at the actual experiments that we did. But if you were to summarize everything, Feynman says that we got two things now. One, electrons behave like a tiny magnet, very similar to how a spinning ball of charge would work. And secondly,
actually said exactly mathematically, it works out the same exact.
They wobble, and they show that they have angular momentum.
And somehow they don't spin, though. I used to think that they didn't spin too. What an idiot if I knew they were saying this crap.
How do you reconcile all of this?
Yeah.
There's only one way. We have to say that electrons have some kind of a property which resembles spin, even though they don't really do.
Or we could just say they spin, you moron.
And even the math shows that the tiny magnets that they produce, the strength of the tiny magnets, which is technically called the dipole moment, but don't worry about it, it is directly proportional to its the quantum angular.
Yeah, it's exactly the same because it's freaking spinning, you moron.
Momentum. So there is no escaping it. It is evident that the electrons possess some kind of a quantum spin, and it's that quantum spin that gives rise to these tiny magnets.
Yeah, just wait till you hear about quantum states, and just wait till you hear the next video. This woman makes him seem sane.
The magnetic dipole moment. We can ask Feynman, what's the best way to put it all together? Like, how do we reconcile all of this? This sounds very contradictory, right? That electrons don't spin, but they kind of do. Well, Feynman says we need to be very careful with the words, and here's one way, my understanding of what Feynman says. Well, what's the way to think about quantum spin? Well, think about quantum spin that the word says electrons behave just like a spinning top, but it doesn't really spin.
And the reason why we say this is because if you have a ball spinning and smaller parts aren't actually spinning, so if you have no smaller parts, that you can't spin the ball itself. Bull.
And I asked Feynman, well, Feynman, how do I make sense of this?
Yeah.
Feynman, how can something behave like it is spinning even though it's not? I don't have an intuition for this. And Feynman would tell us, remind us that, Mahesh, how can you have an intuition for a world that you're not exposed to? Our intuition comes from our limited understanding.
this bullshit where you just can't understand it. It just sounds crazy, but if you don't have smaller parts, doesn't matter how big you are, you can't spin. It's a bunch of bull. This is Looking Glass Universe. Spin in quantum mechanics. This is where the insanity goes. Let her tell her facts first, and then we'll get to the crazy part.
Charged particles, like this negative electron moving around, causes magnetic fields. This is an insanely deep and beautiful result from classical electromagnetism. That's why it's called electromagnetism, because it showed that electricity and magnetism are not really different things. They're actually kind of the same things. A charged particle moving is what causes magnets. Now this is an important result, but it was known by the time that people were coming up with quantum mechanics, and so of course it was baked into quantum mechanics. We'll very soon see that in quantum mechanics, electrons are not described as point particles like I like to draw them. They're actually more like waves. Very similar to light waves, they're spread out in space.
No, your ability to see them because they're so tiny and moving is what is blurred, okay? It's not that the electron is blurred. Your view, this goes back to frame of reference, man. Your view is blurred.
And this is true even when they're inside of an atom. Instead of a single point particle rotating around the atom, you have this cloud of electron all around.
Keep in mind, I used to believe this bull crap. Just wait till you get to the end.
All the time. But even though it is this wave that's spread out, it still has this thing called angular momentum. So angular momentum in classical mechanics is what you get when something is rotating. And electrons around the atom do have angular momentum. And so using what we just learnt about electromagnetism, we would expect that this electron that has some angular momentum around this atom also does produce an electric field.
Magnetic
and that
field.
Is correct.
You can see she said magnetic.
In quantum mechanics. So far, so good. But spin is different. Spin wasn't originally baked into quantum mechanics because people didn't expect it to happen. It doesn't seem to arise from the motion of an electron in the same way that the angular momentum around the atom does.
See, she's basing it on this fact, and I used to believe this crap. She can't see the electron, okay? She only has, because it's so tiny. So because she has a blurred view, because her frame of reference says it's blurred because it's so tiny and moving, then that is real, okay? No, it's not real. It's your perception is real, okay? The wave as a perception is real, but it's not. It's a point part. It's a particle, okay? It has mass.
It seems to be an intrinsic angular momentum. When physicists first encountered a type of angular momentum that electrons have that couldn't be accounted for by the electron going around in circles, they modeled it this way. Imagine this electron is a lot like the spinning Earth. There's an axis of rotation and the electron spins about there. If this electron really does have some physical extent like this, it really is the same as a charged particle moving in a circle. Imagine that this is the bird's eye view of this same electron, right? And it's spinning around this axis. That means that if we looked at any little piece of this electron, say this piece, then what happens to it over time? Well, it spins in this circle. It goes around. And so that means that this is a case where you have a charged piece of material moving in a circle. That means that this should create a magnetic field. In fact,
It does create a magnetic field, not because that little tiny piece, okay, because you can't quantize the charge.
Important result.
I mean, yeah, I said that opposite. You can't, it's quantized. You can't take parts of it, okay?
About charged particles like this with physical extent that are rotating around is that their magnetic field looks a lot like a bar magnet. So the magnetic field of a bar magnet will look something like this.
See, keep in mind, the whole time she knows that this is a little tiny magnet. She admits it all the time. She just won't admit that it's spinning. That's not the whole point. I don't care if it's spinning or not.
Sort of like the magnetic field of Earth, actually. Which, now that I think about it, isn't unrelated, since the magnetic field of Earth is also created by charged particles inside of the Earth rotating.
That's all they do is prove that they're wrong, and then they say this proves I'm right.
That's kind of cool. So yeah, you get this kind of magnetic field from both objects. This is something that I got wrong in my original What is Spin video that I corrected later, but I feel like I want to correct here as well. These two things are very, very similar, like their magnetic fields are almost identical, but there is a big difference between them. This has angular momentum. This does not. This is...
Is she retarded? It's made of these, and if these are rotating in there, then they are making the magnetic whatever, right? And if you know, if you have iron or whatever, that's what they do. They line up their north and south so that they get a magnetic whatever field. Yeah, obviously the magnet is not rotating, but if this is rotating and it's in there, then yeah, that's what's creating the magnetic field. They're exactly the same. It's made of these are made of atoms which have electrons. Is she being serious?
It's just a magnet sitting there. This has angular momentum. The angular momentum does make a difference because the results we're about to see of the Stern-Gerlach machine do not happen unless you have angular momentum. So the Stern-Gerlach experiment involves this massive magnetic setup where these two things are magnets with a very particular magnetic field. And then you shoot electrons down this path, and then you measure where they end up on the back wall.
Oh, we all know these are like really giant magnets. Okay, we all know if you get a tiny magnet, which she's saying, electrons have a north and a south. They're tiny magnets. Okay, they all say that, by the way. 30 people. They're all physicists. They're all saying it. Okay, they all know that it has the it has the north and south, right? That's what the up and down is, okay? North and south, all right? So she knows, if you throw I want to ask you, if you throw a magnet that had north and south, and they were just randomly, this way, some that way, you're going to get 50% go to the north and 50 go to the south, okay? Because even the ones that are perfectly aligned, they have to pick, start rotating, and then they'll get sucked up to the top or the bottom, right? We all know this about magnets, right? Little tiny magnets. They will not go through here. They're going to be going to one side or the other. That's a fact. Okay, 50% will be on top, 50% on the bottom. If they're all oriented in all different ways or whatever, random ways.
So this back wall is able to detect where an electron landed. So what do we expect to happen if we have a charged particle that's spinning on its own axis? Well, a charged particle like this that's spinning around this axis,
yeah, so the top is the north and the bottom is the south, okay,
can have that axis aligned in many different ways, forward, backwards, like this, like that, and all of those ways will have slightly different results. If the magnetic moment happens to line up with the direction of this Stern-Gerlach machine, then the electron will be pushed upwards very strongly, and so it'll go more up and up until it reaches the back wall quite high up. So in that case, it would end up here. But if the magnetic moment was lined up so it was in the opposite direction, then it would be pushed down very strongly.
Yeah, if the north is point down, it's going to go to one side, and if the north is point the other direction, it's going to go in the other direction. Yeah.
Land quite far down. If the moment was aligned perpendicular, so just flat, then it would not feel any force at all, which kind of makes sense.
It makes sense that if you put your magnet with the north and south parallel to the magnets, that there will be no force. Is that how everyone? I can't believe this.
It's like halfway between feeling a force upwards and feeling a force downwards. So it just feels no force at all, and it would end.
Is that how? I'd like to see someone put a magnet in between two giant magnets so perfectly that it doesn't go to either one.
Of course, there's many other orientations that this could have. So if it was a little bit like this, then you would expect that instead of feeling no force, it would feel a little bit of force, but not enough to make it go all the way up here.
No, it would rotate it so that it